Namaskar friends, today we will be learning about Dijkstra algorithm. Hope you have learned about the Java, the core Java basic concepts. That includes the implementation of core Java class, objects, and the functions writing, how to call a function. So today we will be starting with the Dijkstra algorithm. This Dijkstra algorithm is a famous greedy algorithm. Greedy algorithms means we are repeating till the path has been completed or we have reached the destination. It is used to solve the single shortest path. That means we have the start point and the end point, and we are having a different paths, but we are searching for a single shortest path which we can reach to the destination. It computes the shortest path from one particular source node to all the remaining nodes of using the graph. Though also it will be using the graph as a data structure to store. What is a single source destination path? It is just like the finding the source shortest path from the vertex V to all the vertices in the graph. See, in this example, we are having a source as 1, this 1. This one we can say this is the source. So we can say this is the source, and we have to reach to this destination 6. So this is the destination. We can traverse through 1, 5, then from 5 to 4, and from 4 to 6. So this is the first path we can follow. We can have another path also. We can traverse to 1 to 2, 2 to 3, 3 to 4, and 4 to 6. So this can be second path. And we can have another third path also, which we can follow from 1 to 2, 2 to 5, and from 5 to 4, and from 4 to 6. So this can be our third path. So we can have multiple paths from one source to the destination. If we compute from 1 to 6, we have to reach. So we are in the first path we are having 1, 2, 3, and 4. 4 nodes we are traversing. From second path 1, 2, 3, 4, and 5. 1 plus node. So in the second we are having 5. In the first 1, 2, 3, and 4. And the third one 1, 2, 3, 4, and 5. So this will have the 5 nodes. So which is the shortest one in which we have to traverse less nodes? This first path. So this will be the first shortest path. So what is the application of area of this Dijkstra algorithm? Majorly in the real world, we are implementing this Dijkstra algorithm in two. Number first, in the Google Map for the map traversal, and we are using it in the routers to traverse from one network to another through the routers. So these are the two application areas where we are using this Dijkstra algorithm to find the shortest path from source to destination. Say this is my source and this is my destination, so we can reach through this to this, from here to, or we can have another path also. If these two are connected, then we can go from here to here, and here to here. Then if these are connected, so these are the application areas where we can use the Dijkstra algorithm. So what the Dijkstra algorithm actually is, it is for finding the shortest path in the graph theory. What are the basic things it can work on? It can work on both directed and undirected graphs, okay, which we have the direction and without direction. All the edges should be non-negative weight. It means there must not be a negative weight. What input we provide to the algorithm? We provide the graph with the edges and the vertices, and the source vertex node which has all the edges and the weights are non-negative. So what will be the output? It will give us the path from source to the destination with the vertices. How? What is the approach we are following? First, in the first part, what we will be doing is we will be computing the distance from u to the v. That means the source to the next nearest node. Then what we will be doing is we will be creating a cloud which keeps the track of the vertices, the distance we have computed. Then we will traverse all the vertices that we have that path for. We will label them with du, as this is the distance we have to follow from v to reach u, and then we will compute the smallest path, so from v to u. When we are computing the smallest path, we will find the minimal path that we have to follow from source to the destination u from the du, and this is the final. This is a small pseudo code that can be easily learned. So first what we have done is we have initialized all the vertices with infinity as a distance, because we don't know what is the distance from source to that particular node. Now we will take the weight for each and every known node, and then we will mark them with the distance. Yes, this is the source from the distance, and these are the nodes we have to traverse. There is this weight, and we will calculate. Then after that we will find the smallest path and from the previous vertices, and then we will finalize and reconstruct the path from v2 back to the v1. Now we will take a small example. Suppose that we have this small graph where we have, I will change the color. This A is the source. So we have learned that first the source will have the 0. Okay, so we have written 0, and all the other nodes will have infinity. Yes, we have initialized them. So the first part is done, initialization. All the nodes are now initialized with infinity. Okay, now we have all the nodes with the vertices as infinity and the source as 0. Now we find the next nodes that we have. Okay, we have the A to have, we have the path to B, and what is the weight? 2. So what we have done is we have given weight 2 to it. We have the next node D, which has the weight 1, so we have given 1 to it. Oh, now this is done. But what is this C as infinity? Why? Because there is no direct path from A to C. We can go from here, but there is no direct, so that's why we have put C as infinity. Next, we have traversed A and D. Now what is the minimum? D. So from D we have to move to the next node. So the vertex in the list with the minimum distance is D. Yes, rest others are not been touched. Now what we will do, from D, which node we can reach? We can reach to C. We can have the path to E. We can have the path to G. We can have the path to F. Okay, so from path to C, 1 plus what is the distance from C to D? 2. So the total distance is 3. To node this E, we can reach from 1 plus 2, 3. We are given F. If we go directly from here, 1 plus 8 is 9. See, this G, 1 plus 4 is 5. Okay. Now, you are happy that we have done everything? No, I have not done everything. We have to update, because to reach F, we have two different paths. We can go from here and we can go from here and here also. We will update this in the next step. Okay. Note that D do not update. D is 1 only, and E is already known. This, okay, 3. Nothing updated. E is not updated since it is the larger than the previous one. It is larger. Yes. Okay. No issue. Now there is no update on the E, because if we go from here we can reach here only. Or if I follow this also, 2 plus 3, 5, and 2, 7, this is larger. So this is the shortest 3, okay, no issue. And G, 4, no issues. We cannot move from here and there, because if you add 2 plus 6, 8, 8 plus 1, 9. So it will update to 9. No, we don't want the big path, we want smaller path. Okay, now we have to update this F. How? See this F, the distance we can reach from here and here also. So 1 plus 2, this is 3, 3 plus 5 is 8. So F can be updated as 8 also. Previously it was 9, but now it is 8. Okay, now we will update it again. We will again find the minimum. We can reach to F from here also. 1 plus 4, 5. 5 plus 1, 6. So which is minimum, 8 or this? So the minimum is 6. So now the F has the weight 6. So we will pick the smallest cost to reach F is 6. Okay. Now I think this is clear. So we can reach from A to F through A, D, F. A, D, G and F through the smallest. Okay. Now we will write a small pseudo code so that we can check what we have done and how to represent it. See, this is a small which we have the graph, weight and source. So for each vertices V, so first what we have done is all are initialized with infinity, source is 0. Now we are checking the discovered nodes, we have checked, so we have updated the vertices and we are extracting the minimum through and iterating till we have reached to the minimum. Now we are relaxing the nodes. Relaxing the nodes means we are checking each and every adjacent node and finding the minimum path for this, and we have got the final. So the programming is not complete until we write the algorithm. We have to write the algorithm also. So we are writing the algorithm. So first what we will do is we will set up a shortest path tree for this, and we will keep the track of the vertices which includes the shortest path with the minimum distance. Okay? Remember this minimum distance is very important. It can be finalized. Okay, this set is empty. So what we have done is first we have initialized all the nodes with infinity and the source as 0. Now in the third step what we are doing is all the edges vertices which we have covered the infinity will be taken from there and checked with the minimum path which has and their distance, and we update them. Okay, now what we will do, we will again set a path inside it and we will check for the adjacent vertices to the U with the minimum path and from the source, and the weight should be always be less. Now we have got the algorithm, we have understood with an example. Now we'll write a Java program for that. So for the Java program, first we will create a class with the name shortest path. This shortest path class, for this example we are taking the VS9 so that we have the 9 nodes. Okay, now first we will write a function with named as minimum distance. This will calculate the minimum distance from the what? Yes, very nice. The shortest path tree. Initialize the minimum as an integer with max value and minimum value as -1 so that we have the initialization. Now what we have done is we have looped it with the set B and the false for all them, and we have used the AND operation so that we have the minimum of this, and we return the minimum index. Now we have found the minimum index. Yes. Now we will create a function to print what we have. So we are using this function which will take the input as the array of the constructed distance, and n is the number of nodes. Okay, it will print. This is a simple SOP. Okay, this is the main algorithm that Dijkstras we are implementing through a adjacent matrix representation. Okay, now we have created an array with the vertices v, 9 we have given, so it will create a 9 source with 9 boolean. This is the shortest path we have created for the array. Okay, now what we have done is we have used this for loop to initialize this. The distance source is 0 first step. Okay, now we are calling to update all with the infinity, and now we are checking the minimum distance. This minimum distance function we are calling where the distance which we have got and this shortest path. We have passed this, it will return the minimum. Then we will use this for the true. We will have a loop which checks for each and every node. The smaller than the current value, it will check, it will update. If it is not, then finally what it is doing is it's calling a print solution. Till now we have implemented everything with the class, methods. Now how should we call them? Yes, in the Java we have learned that public static void main is being needed, which will call each and everything. It is the main entry point. Yes, now public static void main graph has been created with the 9 nodes in their weightage. Yes, now what we have done is we have created the instance of the shortest path t. This t.Dijkstra, what it will do, t.Dijkstra will call this method. What this method will do, it will have the graph and the source. It will call the minimum distance, this minimum distance. What is the function this minimum distance? Here, this minimum distance. It will calculate the minimum path. It will pass. Then everything is done. Now it will call this print solution. Where is this print solution is? Here. What it is print? Yes. So now we have to find out the solution also. What is the output? Yes. Here we have the output. From 0 vertex, we have the 0 distance. From first, 4. From second, 12. From third, 19. 4, 21. 5, 11. 6, 9, 7, 8. And 8 to 14. Okay. Now I think we have got the idea of how this Dijkstra algorithm is working, what are its data types, how it is implemented in Java. Okay, now we'll take out the complexity also. What is the complexity? Complexity is the term which is very important. The time complexity means the time required to execute this Dijkstra algorithm, because each and every algorithm or program should have less complexity. Okay, it should require less time and less space. So what is the time complexity? O v square. What this v square is? It is the space required to store the matrix. Okay, and what is the space complexity? Storage space. It is OV to store the distance and return. Okay, now I think without the recap we cannot end the class. Okay, so we have quick questions so that we can have the recap of what we have learned. Okay, Dijkstra's algorithm is very famous for what? Think for it. Yes, your answer is very nice. It is a greedy algorithm. Very good. Question number 2. The distance to keep. The algorithm keeps the track of the set of the vertices for which the distance has been computed. What it is called? Think. Yes, it is cloud. Very nice. The 3rd question. The dash is the, yes, so we to store the distance array. Yes, very nice. It is space complexity. I think everything is clear now. Everything is clear and we don't have any questions and queries. If you have any questions or queries, you can ask me. The time is for you.